Okay, so.
And today I would like to briefly speak about exploratory search, which is quite different to what we are usually doing. And this time I'm not going to convince you that vector search is going to replace your full text mechanism. I'm not saying it's not true, but I'm just not going to speak about that today. But before we start, let's just briefly describe what vector search is and what are the main principles of it. So basically, for vector search, we are using some deep learning models which are able to encode our data, no matter what it is. It might be text, images, videos, whatever you have, and whatever you are able to train the network to work with. You are able to convert your unstructured data into a structured vector representations. So this is, in a nutshell, a different representation of the same data, and that is way easier to be compared to each other. Comparing texts is quite a challenge, but if you are able to create a model or just take an existing pre-trained model, use it as it is, or fine-tune it, then it should be able to convert those two queries, those two documents, into similar representations. So striped blue shirt made from cotton should be somehow similar or even identical to cotton-made maritime shirt, even though the words that you used are completely different. Not completely, but they are different. So if you just compare the numbers at every single position, we have a similar value. So overall, if we just compare the distance between those two vectors generated by the same model, they should be pretty close to each other. And if we had some two-dimensional vectors, this is how it should look like. So basically, the red dot is our query that we want to compare to blue dots, which are our documents, items, whatever you sell. So basically, this is all about proximity. We want to find the closest points. And there are different methods of how to calculate the distance. Quite commonly, we are using Euclidean distance or dot product, but cosine distance is probably the most common one. And if we just put a reference point to that visualization, we can easily calculate the angle between two given points in that space, because cosine distance is all about angles. And this angle determines, this angle is being used to calculate the cosine value. And this is, in a nutshell, our metric, which is pretty convenient because there is a natural range for cosine distance from -1 to +1. So basically, this is a normalized value that we can normalize even further. So this is cool, but counterintuitive if we just compare the, if we use cosine distance to calculate the proximity, then it might be unnatural that the closest points are not the ones that we could think should be closest in that space, because we are pretty familiar with Euclidean distance. And here, because we assume the distance is based on the angle, those points marked with red would be the closest ones to the query. So that might be counterintuitive if you are just looking at this two-dimensional space. We are usually working with high-dimensional vectors, few hundreds at least, so it's really harder to visualize them. If the cosine distance between your query and document is 1, that it means a perfect match. -1 means completely opposite. It's quite hard to say what is the opposite of a particular document. If you have a particular inventory, you are probably selling some kind of products. So all the vectors you have should be somehow similar to each other. If you sell clothes, there might be different pieces of clothes, but still the vector representations won't be that far away. I'm not sure what is the negation of a piece of cloth. I know that might be just some kind of noise that is converted to a completely opposite vector, maybe a landscape, but definitely that won't happen. But there is a cool idea behind using cosine distance, because instead of performing approximate nearest neighbors, we can convert the problem to approximate furthest neighbors just by negating the query vector. If you would like to find the most dissimilar items based on the vector representations, you can just convert the query vector by multiplying it by -1, and that's basically it, because this will create a vector which will have -1 as a distance using the cosine function. So this is it. This is basically an idea behind this similarity search, which might be quite easily achieved with cosine, but cannot be achieved that easily with, let's say, Euclidean or dot product, just because they might be unlimited. Here we are also looking for +1 as a perfect match. So the closest point should have that distance value. But as I said, it's quite hard to really face this kind of opposites in real life. You would need to train your model in a way that it will be, I don't know, returning -1 if you compare cat and dog pictures. If you fine-tune some existing models, that might be achieved through fine-tuning using triplet laws or metric learning in general. This is also a good insight. If you are using some kind of pre-trained model, it was usually trained in a way that there were some samples provided, and that the model was just said that those items should be similar to each other, and the similarity was calculated using some sort of distance function. So you have a model that was trained for Euclidean distance, you should be probably using Euclidean distance for the approximate nearest neighbors as well. So it's pretty good to know your model before you start using it. If you use any kind of API like OpenAI or Cohere embeddings, then you probably can find that information quite easily in their documentation. If not, then that may require some experiments to find the proper one. But basically, watch your model and know it quite well. And known item search is an area that we are mostly focused on while attending conferences such as Haystack. Probably majority of the problems we are dealing with are related to known items search. And known items search is a problem in which we can define what are the relevant documents given query. So you can say that for a particular query, that should be the set of results that we want our algorithm to return. So, for example, if you are going to switch to the newest iPhone, you are probably going to look for a new cable, just because the old one is not gonna work in your case. And if you are familiar with cables to the extent that you can form a regular query to the system, that would be probably what you would like to search for. But if you are using iPhones for ages and you don't know that there is a different type of cable that you used to buy, then you might be forming your queries in a different way. That happens. It's not even long tail query, it's snake query. I don't know how to call it. And this is basically where vector search shines even brighter, just because there is not a single keyword that we would typically use to describe a particular item. And this is why semantic search comes to the rescue in that scenario. There might be also reverse image search, but still, this is in a nutshell known item search, because we know what are the product, what is the product. Actually, the user know what is the product they are using, they are looking for. And since we know some sort of Qdrant truth, we can calculate different metrics and care about the quality of such a search. So there are various ways. All of them were actually mentioned today, so I'm not going to go into the details. But basically, it's way easier to say that we returned some relevant documents, some relevant items. So that reminds me of those people who exactly know what they want and can enter any store, go to a specific shelf, choose the product they wanted to buy, go directly, pay for it, and exit it without a few minutes. For me, it's not always the case. I'm more this kind of person. Even today, it's my third or fourth time in Qdrant. I'm not sure how to pronounce it properly, but basically, every single time I'm coming here, I still need to find the proper entrance, and I'm exploring the whole venue. I'm not sure. I'm not really good at search, I have to say. But basically, there are a lot of people who may prefer this kind of exploration instead of buying a specific thing. That happens quite a lot. It's not only my experience, probably, but I don't know, if you want to buy a piece of cloth, but you do not have anything specific in mind, I don't know, maybe you are just wearing black t-shirts all the time, so that's way easier. But there are also cases in which you need to buy something, you want to buy something, but you don't have any idea, so you're just hanging around all the shelves in the store and looking for what's available. That happens, and it seems to me like we were neglecting those kind of users in online search for ages, because exploratory search is exactly what I would like to describe today. It happens quite often if you visit a new country and if you are looking for something to eat, then you might be skimming through the menu and just trying to find the proper dish for you. But if you don't know the cuisine, don't know the language, you are prone to choosing a random item that you are not satisfied with. That would be great if we could have a way of providing those users some sort of interface so they can interact with some possible options and choose what suits them best. We tried to solve that with facets. So facets were used to perform this kind of exploratory search, but that assumes we have some sort of query. And if I query for an iPhone, for a smartphone, then I'm just displaying facets which are related to this kind of inventory. But that's not the case. If I go to a new website that I knew nothing about, then I would prefer having a way to explore what they are offering to me. Facets may give you some sort of intuition of what is available, but in general case, if there is no query, it's quite hard to display anything. You might be serving the default set of categories. That's it. And exploratory search is actually nothing new. If you were watching movies on VCRs, then you were also probably going to some rental videos like places, and you were just seeing what's available. You didn't know much about the titles of the movies you would like to watch, just because there was no internet back then, and we were only looking for some cool covers just to bring them home and be disappointed once again. That happened a lot, for me at least. So that's definitely one of the search problems that actually was partially solved, because we have those recommendation systems, and there is already a way of, if you use Netflix, HBO Go, a different streaming platform, then you are just served with a set of items that might be just relevant for you. But if you would like to escape your bubble, then there is no way to do that. Instead of creating, let's say, a new account and trying again, other than that, you would be you need to know that you are looking for a particular item, because otherwise you would need to just skip through all the available items, all the available movies in a specific platform, and that's basically it. So this is not a new concept, but measuring the quality is way harder, since we don't know the ground truth, and this is a personalized experience. Everybody can have their own preferences, and it's quite hard to tell what is relevant if there is no query. What is relevant for all the users? There's not such a thing. So basically, this is a tough to measure. Maybe we can measure the quality of our exploratory search using some business metrics like the revenue in those scenarios in which people didn't start with a particular query in mind. But this is way harder, and I don't have a clear answer of how to do that properly. And there is another concept which is related to exploratory search, which is this similarity search that I've already mentioned before. If we had a way to find items which are dissimilar to a given one, then we could also take care about the diversification of the search results, because we won't be serving some random items, but instead just providing some items which are in some sense dissimilar to the already presented ones, and that should allow us to bring diverse results and start the journey in a proper way. So this is what all exploratory search with based on vectors is all about, and it's hard to be reproduced with full text search, but it's quite easy to be done with cosine distance on vector embeddings. This image is no longer a two-dimensional space of embeddings. This is some sort of projection, so it's not based on the angles anymore. But in a nutshell, I hope you get the idea. We are looking for the items which are farther away from a given query. And the dissimilarity search solves not only exploratory search, but also can help us with the data quality, because we might be also struggling with that. And that's a great tool to solve it at least somehow. So your items, your inventory is probably somehow divided into some categories. So this similarity search may help you with solving mislabeling because there is a distance measure that can tell you that a particular item is further away from the other items in that particular category. What may subcategory or a different one, depending on how you structure the items in your inventory. But that might be also applied if there are no labels at all, because outlier detection might be also done using this approach. So this is pretty interesting because that solves not only exploratory search but also data quality issues. And coming back to the diversity search, there are actually two different ways of how to approach it. First of all, the simplest and most naive one would be to serve some random items whenever we do not have a query. But there is an issue with that approach, because if we did that, our sampling would be biased toward those type of items which are more frequent. If you sell shoes and 90% of your inventory is shoes, then you would be probably serving all the suggestions coming from this particular category, and nobody will ever receive an item from different categories, or it would be really rare. So this is a naive approach that won't work that well, but there is also another similarity-based sampling in which you are performing a sequence of actions. You are selecting an item, and then in another iteration, you are just selecting another item which won't be that close to the already selected items, and that continues until you reach a number of an expected number of results that you wanted to return. So you start with a random point, select one item, and in another iteration you are including the previously selected item to select something which is far away. So by using that approach, we are comparing the results to the previous ones, and finally getting a diverse set of results just because we incorporated the previously selected selected items into the search process. It's worth mentioning that we do not compute any new embeddings within that process. We are only relying on the embeddings which have been already indexed into our vector search engine. So it's way faster, because creating the embeddings is usually the bottleneck of that whole process. That takes some time, usually requires some GPU power. But if we just rely on the ones that we have already indexed, this is pretty okay, because that should be fast enough. And one thing to notice here is that we are performing a sequence of vector search operations. That means if you want 10 results, you need to run vector search 10 times in a row, and that cannot be parallelized. Maybe you could split it into 2 groups or whatever, depending on how many results you want to have, but still there is a sequence of actions that increases the latency. So we need to have a way of speeding up the vector search phase if we want to do that. There are different methods like scalar quantization. So instead of using float 32 to encode your data or float 64, we are just converting those numbers into 8-bit long integers, and that should speed up the retrieval process, just because we are comparing shorter sequences of numbers, and that may improve the vector search even up to 4 times if we do that for those data types. So this is pretty okay, because we are able to speed it up a bit. But if we just want to push it to the limits, there is also a relatively new mechanism. We have just introduced that into our offering, into Qdrant APIs. You can use binary quantization. So instead of converting your floats into integers, you are converting them into booleans. So that simplifies it a lot. You can gain even 40 times faster retrieval, but that works not for all the embeddings which are available out there. You need to choose a proper embedding provider and experiment with your data. Those 2 models that I mentioned here are working pretty okay, and with additional oversampling. Oversampling means if you request 10 results from vector search to be returned, we are getting, I don't know, twice as much. and then perform the additional round of similarity search, but using the original embedding. So that improves the recall and simplifies it a lot. You can gain even 40 times faster vector search. So it stops being a bottleneck anymore. And diversification of search results is an area which seems to be like if it was neglected. There are some pretty old approaches to do that. This paper, I really liked this paper when I was preparing those slides, but basically this is the one coming from 2009, which is pretty old, I have to say. And there are not that many attempts to solve it. But the conclusion is solving the problem of search result diversification, because this is how this problem is called, is NP hard. So we need to look for some approximate solutions if we want to do that. And there is just one method which is quite commonly being used, which is called maximal marginal relevance. If you use LangChain, for example, this is built in already. This method is quite simple, but this is a greedy approach, just because we need some sort of approximation. And I would like to present the overall idea because it's fairly simple and might be implemented even without having a huge overhead generated by using so heavy libraries like LangChain. So this was proposed back in 1998 in a paper. I just put the title here. And the main goal of that process is to decrease the redundancy and increase diversity in our search results. And the procedure is quite simple. If we want to extract n documents, we extract significantly more documents in this initial phase and then do some sort of re-ranking. And this re-ranking is greedy because it strongly relies on the order of the iterating through the set of results. So R is the set of results retrieved by this initial procedure. S is a set of items that we have already selected, and now we are just iterating through the unselected items, and we are selecting the item which maximizes this formula. And we need to iterate through this set as many times as many results we expect this procedure to return. So if you want to have 10 results, we need to do it 10 times. But this is basically quite simple. The first term here is all about the similarity of the query and a particular document. And the second term is about similarity between the documents, between current document and the documents that we have already selected. So in the first iteration, we are just taking this first item, the most relevant one, just because there are no other selected documents yet. So we are just maximizing that, and this is already maximized because this was returned by the vector search phase. We can also apply this constant here lambda, which is which actually allows us to control how diverse will be our results. So if it's set to 0, we are not going to consider the similarity of the query and the documents at all. If it's set to 1, we are only taking care about that one. So in a nutshell, this is like taking top n relevant results. So that repeats a few times, but this is fairly simple procedure. As I said, this is a greedy one because the first item is always going to be selected, and that doesn't mean the diversity of the search will be as high as possible. But there is also a different approach, which somehow reminds me the recommendations that might be achieved with vector search. Usually they are done in a short term, because the user preferences might be expressed as some sort of average vector of the items they have already bought or they just simply interacted with. So let's say we can also generalize that to liked and disliked or positive and negative examples. So those green dots represent positive examples. So the items that this particular user could possibly buy, watch, whatever we want to achieve. And those red are those that this particular user ignored or didn't buy or just drop basket at this point, or just gave us some sort of feedback. That's also possible in some scenarios. I don't want to watch this kind of movies. So we have direct information from that particular person. So we can use that to perform a vector search and form our query using some sort of combination of the original embeddings, because those are the already embedded documents in our database. There is no query that we need to vectorize and create an embedding from. We can create centroids by averaging those positive and negative examples separately. Those centroids might be then used to create a single query. We need to combine them somehow. So if we have a positive centroid and negative centroid, we can move the positive one in the opposite direction of the negative one. So this is how the final search query can look like. So this is basically one approach, how we can handle that. Right now, it's just a simple vector search, a single pass of vector search, because that's obviously just to find the. If we just run the vector search once, we will receive a bunch of relevant results, right? But all of them will be somehow similar to each other. If you want to make sure that the results are diversified, we still need to perform that procedure. Again, this similarity-based something has to be done sequentially. So in the first call, we are going to retrieve results which it might be just a random result, or I don't know, if we have a goal to sell a particular item, then we can promote it. That might be a rule that we will hard code into the system. That doesn't matter that much. But in every next call, we are just going to use the results retrieved by the previous calls as negative examples. And those negative examples will make sure that we are receiving vectors from different subspace of the latent space of our vectors. This is basically a simple procedure that we have already implemented. There is a recommendation API, which is, I have to say, highly underappreciated. There are not that many users right now. I don't know why, because this is pretty interesting. And that was available in Qdrant since the very beginning. So here you don't need to vectorize your query at all. You are just providing the IDs of the vectors, of the positive vectors and the negative ones, and this is all being averaged using that procedure. You may also notice that we are using positive vectors twice, and that might be not that obvious, but basically Qdrant emphasizes those positive examples. Actually, the current implementation restricts that you need to have at least one positive example. We are working on that, but basically this is an idea of how this is gonna work. So we have some positive examples and negative ones, and there is some averaging happening, but still we emphasize the positive ones a bit just to make sure that they are this feedback is also included. There is an interesting article I just want to briefly mention. This is all about averaging the embeddings, pretty cool one. And there is a demo that we have implemented recently. This is all about food recommendation. This is quite interesting that we have 2 talks in a row which are about food. It's great that we just finished our lunch, because that could make you hungry. But basically, this is a fairly simple open source application that uses different methods to provide this exploration into food discovery, something that you would really appreciate if you were visiting a completely new country without knowing its language. You are shown some random items at the very beginning, and then you can give your feedback just to get closer and closer to what's interesting for you. There is also a textual search if you want to start with flatbread with toppings. If you happen to not to know the pizza term, you might be looking for this kind of dish. Still, that's possible because it's all based on semantic search. And there is also an option to find a restaurant nearby. I just need to speak with Delivery Hero. I guess we have a deal to make here. Basically, this QR code links to the online version, but you can also fork it and play with it if you want to. But this is not the only method that might be used to achieve the recommendations or incorporate some negative examples into the vector search. there is a different approach based on relative distance in which you can provide some negative samples, and those negative samples are used to make some exclusion areas during the vector search. So when we are using, there is a HNSW graph under the hood that is being used to perform this proximity-based search. And if we make those exclusion areas, our system will be more prone to get in an opposite direction. So it will be omitting those areas to provide some results which are far away from those points. So this is also pretty interesting. This is a relatively new idea that we are currently working on. So this will be included in hopefully in the next release. So within a few weeks, that should be implemented as an extension to the recommendation API. And finally, you won't be expected to provide positive example, at least one positive example, but you will be able to provide only the negative ones, and that should be pretty okay. So this is it. If you have any questions, I would be happy to answer them or discuss them today or tomorrow, because I'll be still at any Haystack. Thank you very much.
Okay, thank you once again, Kacper, for the talk. I guess we do have questions for you. Starting the first one from the group.
Thanks for the talk. You mentioned binary quantization. So can you speak a little bit about that? Like, how many floats are you encoding in a single, I assume, bit? And also, can you share some intuition about how is it possible to preserve semantics from the original vector while compressing it to such a tight space?
Yeah, sure. So basically, one float is converted into one bit. So this is it. So 1 byte is built from 8 floats. And that works only for specific embeddings, the high dimensional ones. As I mentioned, the OpenAI model works pretty well with that. If you apply this over something, that's what I forgot to mention actually. But basically, the more dimensions you have, the more redundant they are. It seems like it works for longer embeddings, and those were just 2 examples that we were able to test so far. If you use, I don't know, sentence transformers and all LM mini V2 model, then probably that won't work that well. It's still under experiment, but the feature is already available if you want to test. But that requires experiments and works. Well, OpenAI embeddings are over 1,500 dimensions, so they're pretty long. So that compression works for them pretty well, but not for the shorter embeddings.
Cool. We have one question online. Could you please clarify how you use the average liked and disliked products for the subsequent vector search? Not quite clear how they are transformed in a vector search input, since those are 2 different points in the search space.
Okay, so this is the formula that is currently being used. So basically, we are averaging positive examples and negative examples, and this is a formula that we use to create this query vector. So those positive and negatives are simply converted into another vector, which is used as a query. So we are averaging the negative vectors, averaging the positive. Positives are used twice. And this is a simple formula. This is how it's implemented under the hood. I'm not sure, like, if I can describe it a bit clearly.
Okay, I hope, so Mario asked this question. I mean, I would urge him to ask a follow-up question if it is still not clear. Okay, so we have one.
So maybe just clarification question here, just to make sure I understood well. So actual diversification of results is a result of multiple vector queries on the,
Exactly.
And then you're just doing a vector selection so it covers equally, or covers the space evenly.
Yeah, exactly. That has to be done as a sequence of vector search operations. So first of all, we start either with random point in that space. We can just choose one of the documents, or if there is a rule that we want to use, we can also select the one we want to sell, and then a subsequent call will use that particular item as the negative example.
But, okay.
So we'll be using the rest of that space and trying to find the most dissimilar item to that one. And in the next call, we are going to use 2 negative examples,
But can you comment on, like, you know, how computationally expensive this is? Because if we really want to have diversified, and if we need to do like 10, 20 different calls in order, is this really going to be feasible for real-time
Yeah,
search?
definitely. That's because we do not create any new embeddings. You have already all the documents embedded and indexed in your collection. So you are just selecting an existing embedding. So this
But
is
it's
pretty...
still like, you know, instead of doing one vector search, you're doing 20. So
Yeah, but still in the vector search, the bottleneck of the vector search, if you need to vectorize your query, is to create the embedding out of your query. The vector search phase is pretty straightforward if you already have it. It's fast enough to do that as a sequence of actions. And if you apply this quantization mechanism, it's even faster with binary quantization, even up to 40 times. So you can do multiple calls in the same time like it would take for a single call without this quantization, right? Well, as long as you don't want to have, I don't know, like thousands of items returned, then that should work pretty well. Okay, I agree. But if you want to serve, I don't know, 10, that's completely feasible. That's just a few calls more than usually.
Okay, so we do have one more question online. So to speed up diversity search beyond quantization, could we also pre-cluster the data and pick the top item from each cluster?
Yeah, definitely. That sounds feasible. Maybe even using this HNSW graph that is used. Well, HNSW graph is based on proximity. So basically, if we could incorporate those points somehow, like those higher level points that are used as centroids, then that might be also pretty fun. Actually, we haven't done that yet, but that sounds like an interesting experiment that we could conduct.
I am just curious that you showcased MMR. Do you have any working examples on Qdrant to play around with it?
Not really, except for some. There are definitely some examples of using LangChain with that, because this is already built in. I do not encourage you to use LangChain for that. If you are doing search, this is a huge overhead. Even though I'm in top 20 contributors of the library itself, I do not recommend using it yet in production. This is cool if you want to experiment quickly. So there is an example of using MMR with LangChain that shows the idea. Not recommended using it in real life, but this is pretty simple to implement.
Sure. Okay. Any more questions here? Okay, we have one at the back.
So, hi, first of all, congratulations for the presentation. It was great. Just one question. When you do the similarity search, don't you take the risk to get something way too different depending on what you have in your data set? I mean, for instance, you are selling a large variation of products, and you see one like I don't know, a cell phone, and then you recommend something like, I don't know, toilet paper or something completely different. Don't you take the risk, or that would be kind of desirable for the method?
I would say that's desirable in that case. I'm not claiming that you should replace all the search system with this kind of approach. This is like an addition to it. So if you have some users who don't know how to formulate the query because they don't know the domain, I don't know, they don't know the language, or they are just unsure what they want, this might be like an idea of how to present them an interface that would allow them to interact in very. So this is desirable. So you want to provide diverse set of results so they can find if there is anything interesting. So the more diverse the results are, the best it is hopefully for you, I would say. So this is not like a replacement for keyword-based search. It's rather a different interface that hopefully is going to drive you some more users who wouldn't be able to use the system if you would expecting them to form this query. So this is an addition, not the like primary functionality of it.
Thank you.
Any more questions here? Okay. Oh, you have one too? Oh,
Hi. I think in the end you mentioned something about relative distance recommendations, right? And you talked about defining these exclusion areas. So how do you choose these negative examples?
Those have to be provided. Like, as I mentioned, this is like a sequential process. So we start with a random point, and then we want to explore the rest of that space. So we want to find some points which are far away from the previously selected examples. So this is a sequence of actions. You choose a random point or a fixed point, whatever, but you need to have at least one. And then you are sequentially putting some additional examples into the set of results. So this is basically just an idea of how to find these similar examples given those negative ones. But they come from the previous interactions with the system. They are not provided by the user themselves, but it's rather about, we selected this item in the previous iteration. Now we want something which is not similar to it.
Okay. We can take one last question if anyone has one.
Yeah, there is.
Thanks a lot. Yeah, thanks a lot for the great talk. I have a question also regarding this random sampling. So you said random sampling for BM25 is bad because then you get these clusters, or if you just random sample across your whole assortment, you get clusters. You don't want this. So that's why you want to have this in different areas of the space. Have you thought about I just sample 100 completely random points in the space and then take always the closest product to all of these 100?
Yeah, that could work, but basically if you want to diversify your results, then that would be still biased towards those items which are more frequent. Let's say, if I would use the same example again, if you sell shoes and 90% of your inventory are shoes, then you would be serving 90% of those, let's say, recommendations coming from this category.
But only if the shoes are distributed over the whole space. If they're all in one corner and I have points all over my space, then I get again a good sample across the whole assortment.
Yeah, basically that's what this MMR is doing. If you have, if you just run this vector search once, or any kind of search once, then you are retrieving this diverse set of results using MMR. That's actually the procedure which is usually used to combine with if you use MMR. So yeah, that's actually something that might be considered. The other scenario I was talking about was about improving this diversification even more. So how to achieve better diversification just because we use several queries, and this is a sequential process, unfortunately.
Thanks.
Okay, people. Well, thank you once again, Kacper. Let's give him a big round of applause.